All right. So the outline of my talk is kinematic source modeling used in physics-based ground motion simulations technique. And then I'll talk a little bit about the dynamic rupture modeling that is used to constrain some of the kinematic rupture parameters. And I'll show an example of focused on Ridgecrest earthquake. And then I'll demonstrate an application of the deterministic approach that we used in ground motion simulations. I chose a very interesting scenario earthquake. And then we will discuss a little bit challenges and needs for improvements in our models. So as everybody knows now, we use several approaches when it comes to generate ground motion. We can classify them as the ones that use deterministic approach, stochastic approach, or hybrid ones. I think the deterministic approach is the one that is taking lead now because we do have a better understanding of physics of the rupture. We can handle the high frequency ground motion simulations using high performance computing. And on the right side, I show a schematic view of the ingredients that goes into those ground motion simulation technique. But given the focus of my talk, I think one of the ingredients that is very important is the source model. And as Marty explained very well, we need a very detailed knowledge about the rupture model so that we can accurately represent the ground motion at a given point. So when it comes to modeling the earthquake, usually we use the so-called kinematic source. And of course, that is based on empirical knowledge. So we start with magnitude and tectonics. But then there are some very important parameters that I single out: the slip distribution, rupture initiation time, and slip rate. Those are parameters that really needs some physics-based modeling to actually quantify and actually find out what are the relation between them. And so here I'm trying to explain very briefly how one of the rupture generators work. This is the rupture generator proposed by Graves and Pitarka. In the case for past earthquakes, we start with an initial slip, we smooth it, and then as Martin explained, we add some stochastic variability in space using the K square wave number. And the technique is basically what my and Beroza proposed. Now, when it comes to rupture models for scenario earthquakes for a single realization, we go directly to a slip distribution using the K spectrum. But of course, there is a lot of intercorrelation between those parameters, which I will show here. Now, as Martin explained, one of the key parameters that we start working with when we generate a kinematic rupture model is the slip distribution. And so from there, we generate a rupture time. Based on rupture dynamics, we know how to scale it with depth. And there's a weak correlation actually with the slip amount. So there is an acceleration and deceleration of the rupture. We come up with a slip rate function in which the rise time is also correlated with slip. And then the next parameter is the rake angle. So we do have some correlated stochastic variations of the rake angle as it is actually observed in reality. But as I mentioned before, one of the key elements when you do want to generate a physics-based rupture model is to actually quantify those parameters. And we also want to know how they correlate with each other. And so the rupture dynamics can help with that. So usually we start with the stress drop initial model. We use a friction law. In this case, I show the linear friction law. We then use those initial states in the stress drop and embed that into a wave propagation code where the fold itself is acting as a boundary conditions. And as you understand, this is a very computationally heavy simulation based on what is the maximum frequency you're trying to model. Now, there is a lot of studies that have been done in the past regarding the rupture modeling techniques. There are many of them, but it's done a very good job at verification of some of those codes. And also it has tested the performance of them. On the right side, we show an example where we try to model ground motion from the Parkfield earthquake using those rupture models. And I think I have a reference here that you can go and check the latest about this work. We as a group, we also have done some simulations of rupture dynamics for several earthquakes where we try to understand the physics, but also try to grab as much as we can so that we can create these correlations between different rupture parameters. And I'll show one example, which is the Ridgecrest earthquake. So when we start studying the rupture dynamics for any given earthquake, we do need to have a target slip model, which is the one shown here, which is observed by based on inversion of recorded data. But then we need to match not only the slip distribution or some kinematics that was observed, but also the near fault ground motion waveforms, which is shown here. So for the case of Ridgecrest earthquake, we use an iteration technique, which starts with a given stress drop model with a concentration of stress in some areas that kind of coincide with the target slip. And then we do a few iterations so that we can actually produce not only the distribution of slip, but the amount of slip and fit the data. And so from there, we get a much nicer now picture about the kinematic characteristics of this earthquake, which in general is the slip distribution, the peak slip rate, the rupture time, but also the slip rate function. And as Martin explained very well, this is a very important parameter that actually requires not only just one single rupture modeling, but several of them, so we can pinpoint how those characteristics of these source functions are interconnected and how they correlate with the slip. For example, for this earthquake, which is very similar to actually what we observed for Kumamoto earthquake in Japan, we see that the slip rate function is kind of smooth at near the surface. Then it becomes sharper at those three asperities. Actually, these points S6, X8, and X10 are within these high slip areas. But we also do observe that actually the peak slip rate gets higher, not exactly in the area where we have the largest slip, but usually it's in the boundaries and the area where we expect to have high peak slip rate, which also generate the highest energy in the high frequency range, is kind of smaller than what we get from the slip distribution. What's nice about rupture dynamics is that we can also try to understand what are not only spatial variability, but that dependence of the slip rate function. And this is what we observed for this earthquake. And we try to actually improve our rupture generator for generating ground motion for this earthquake. And of course, as I mentioned, in order to get a good knowledge about the variability in our physics and get them represented very well in our simulations, we need a lot of rupture scenarios, realizations for rupture dynamics to actually understand how these different parameters correlate with each other. And you can see that there is a really nice correlation between them for this set of data that was analyzed by Savran and Olsen. But we also noticed that there is a really large peak slip rate variability among those 100 scenarios. There are certain that have really very low, but there are other that are very high. So this is something that we need to capture in our kinematic rupture models when it comes to understanding the ground motion variability within the event or between the events. Now, as a result from this dynamic rupture modeling, we came up with this source time function. And I think Rob Grace will explain how this modification to our Rupture generator on the works in explaining the frequency content of the signal. But I just want to mention that usually the shallow part of the fold does not really contribute to high frequencies as opposed to the areas where we have much higher slip concentration or slip rate. I'll skip this, but just I want to mention that our kinematic rupture modeling has been against different earthquake, and it has been helpful to actually come up with different techniques. This is one that is used in Japan, and Hiromi Yucca is going to talk about it. We came up with a combination of both Graves and Pitarka and Irikura's recipe, and both techniques, they work very well in terms of predicting ground motion. But I would like to spend a little bit more time in showing one example where we kind of go through the whole process for predicting ground motion for a very interesting earthquake expected in the Yucca Fault Basin. This is a basin that is very well characterized, and as you can see, is very complex. We have to consider several geometries for this earthquake. So we start first with preparing the model. So we include the large scale complexities. We do include the small scale of the geotechnical layers. And then at the end, we add some stochastic variability so that we could explain ground motion at months. So we use draping to actually distribute the rupture model on different geometries. And I have one case here where I want to show how the ground motion will look like for a scenario one, which is a curved rupture. You notice that there is a lot of upward rupture directivity effect in this area, but as soon as the waves kind of enter the basin, you get not only a rupture directivity effect, but also basin reverberation amplification that remains strong not only on the footwall, but also on the hanging wall of the fold. And of course, there are areas that really there is a very strong concentration of the ground motion. And of course, we validated these, we compare those with GMPs, and the simulations compare very well. I have to point out that these simulations now can actually do the reverse. We can use them to improve GMPs for cases or mechanisms that we don't have enough data. But I'll skip this part and I'll go straight to the challenges that we are facing and maybe some improvements. So the first one is in rupture dynamics, we really need to, when we go to this high frequency, we need to consider the fold roughness. The folds are not always planar. And I think Kyle Willers is going to talk about it. What we came out is with a two-step coupling approach that is proposed by Ripperger. And what we do, we couple the dynamic rupture with elastic wave propagation that allows you to propagate waves away from the fold. That also allows you to actually use different parameterizations in terms of elastic or inelastic properties of the structure around the fold. And as Rotan and other have shown, it's very important we include more realistic material properties in our fold, because they do actually affect the ground motion. As it is shown here, there's a significant reduction on the near fold ground motion, but also in areas where this ground motion is channeled. And then one nice thing about the rupture dynamics, we could use pseudo-dynamic rupture modeling to actually come up with correlation among different rupture parameters, as is shown in this Schmed's study. And most recently, I think there is a very interesting amount of study that is focused now in developing those rupture dynamics modeling, but using a 1-point and 2-point correlation structure. The 2-point correlation structure, which was proposed by Song and Dalguer and Mai, and later developed a little bit more by Savran and Olsen, is something that is really very important to apply, because it does about how the spatial interdependency among parameters pairs among all the models. And we are using those to generate rupture scenarios and generate some scaling parameters. So as a conclusions, I think we have now a better understanding of the physics of the rupture. We know how to apply to our deterministic ground motion simulation at certain frequency range, certainly between 0 and 5, but now we're pushing to 10. And then for future work, I think we should extend our validations of our rupture, our simulations beyond the GMPs by using new criteria that we are going to talk today. And we need a much more coordinated effort so that this synthetic ground motion can be available to everybody. And we could kind of use a organized scheme to promote the use of physics-based modeling, but also how to get results that are useful to the engineers. And I'll stop here.